Bismillahirrahmanirrahim. Our next theorem, that existence theorem. This theorem states that there exists a basis for a finite dimensional vector space. Suppose that V is a vector space over the field F, be a finite dimensional vector space over the field F. Then by definition, every basis of the vector space V over the field F has finite numbers of vectors of the vector space V over the field F. Let the set S consisting of elements V1, V2, V3 up to Vn, which is a subset of the vector space V over the field F, such that the vector space V is spanned by the set S, as the set S is a subset of the vector space V over the field F, then either the set S is linearly independent or linearly dependent. That is, the subset S of the vector space V over the field F span the vector space V over the field F, and this is a subset of the vector space V over the field F. If this subset is either the elements of the set S is either linearly independent or linearly dependent. If the vector of the set S are linearly independent, that is, the set S is linearly independent, then by definition of the basis of a vector space V over the field F, the set S, when the elements of the set S are linearly independent and span the vector space V over the field F, then this set S is called basis of the vector space V over the field F. But if the set S is linearly dependent set of the vector space V over the field F, then by a theorem which there exists, which state that there exists a vector Vk in the set S, which is a linear combination of the preceding vector V1, V2 up to Vk minus 1 of the set S, then there exists at least one vector which is a linear combination of the preceding vector. This is a theorem. Suppose that Vk is a vector in the set S which is a linear combination of the preceding vector V1, V2, V3 up to Vk minus 1. That is, V1, V2, the linear combination of the elements V1, V2, V3 up to Vk minus 1 gives a vector Vk of the set S. For A1, A2, A3 up to Ak minus 1 are the scalars. Now consider the set S1 containing the elements V1, V2 up to so on Vk minus 1, Vk plus 1 up to so on Vn. Extract remove the element Vk from the set S, and we get another set V1 containing the element V1, V2 up to Vk minus 1. Remove Vk from this set S, we get another vector, and the next vector will be Vk plus 1 up to so on Vn, which is a subset of the set S. And since the set S1 is a subset of the set S, then by a previous theorem, the linear combination of the set S1 is a subset of the linear combination of the set S. Now, if V is an element spanned by the element of the set S, the linear combination of the set S and the linear combination of the set S gives the vector space V over the field F. That is, the element V is an element of the vector space V over the field F by according to this condition, then V can be written as a linear combination of the element of the set S. That is, b1 v1 plus b2 v2 plus up to so on bk minus 1 vk plus vk minus 1 plus bk vk plus bk plus 1 vk plus 1 plus up to so on bn vn. These v1 v2 up to vn, these are the element of the set S, and the linear combination of the set S gives a vector of the vector v of the vector space V over the field F, where b1, b2 up to so on bn are the scalars. Now substitute that b1, b2 up to bn are the element of the field, that is these are the scalars. Substitute the value of vk from equation number first in equation number second. We have, that is we substitute the value of vk from equation number first in equation number second, that is the value of vk is this one. Now that is substitute the value of vk from equation first in equation second. We have v is equal to, equation number second implies v is equal to b1 v1 plus b2 v2 up to so on bk minus 1 vk minus 1 plus bk multiply by, substitute the value of vk from equation first. We have a1 v1 plus a2 v2 plus up to so on ak minus 1 vk minus 1 plus bk plus 1 vk plus 1 plus up to so on bn vn. Now rearrange. We have b1 plus a1 bk v1 is common in these two terms, plus b2 plus bk a2 multiply by v2, that is v2 is common in these two terms, and so on. bk minus 1 plus a k minus 1 bk vk minus 1, that is vk minus 1 is common in these two terms, and so on, plus bk plus 1 vk plus 1 plus up to so on bk bn vn, that is v is a linear combination of the element v1 v2 vk minus 1 vk plus 1 plus up to so on vn, that is these are the element v1 v2 up to so on vk minus 1 vk plus 1 up to so on vn. These are the element of the set S1, that is the element v is also spanned by the element of the set S1, that is these are the element of the set S1, that is v1 v2 v1 v2 up to so on vk minus 1 vk plus 1 up to so on vn. These are the element of the set S1, that is v is spanned by the element of the set S1. As v is an element of the of the linear, v is an element spanned by the set S, also this element v is an element of the set spanned by the set S1. Therefore, the linear span of this the set span by S1 is equal to that is the set span by S is a subset of the set span by S1. Now, from equation number A, that is the set span by S1 is a subset of the set span by S, and from equation number B, the set span by S is a subset of the set span by S1. Therefore, from equation A and B, the set span by S1 is equal to the set span by the set S, and the set span by the set S is the whole vector space V over the field F. Now, Fs1 is linearly independent. Fs1 containing linear independent vectors of the vector space V over the field F, then S1 is a basis of the vector space V over the field F, because S1 span the vector space V over the field F and is linearly independent. But if S1 is linearly dependent, then we repeat the same procedure to obtain a successively set S2, which is a subset of S1, or S3, which is a subset of S2, and so on, such that each subset Si of the set S1 span the set spanned by the set S, and the set spanned by the set S is equal to the vector space V over the field F. According to this condition, that is to repeat the same procedure as above. That is, there exists at least one element which is a linear combination of the preceding element. We replace that element by its preceding element and get a subset S2 of S1 which span the vector space V over the field F and is called a basis F and is and that set is linearly independent set NV. That is, in some stage we reach to a subset of the set S which is linearly independent and span the vector space V over the field F. That set will be linearly independent. That set is called a basis of the vector space V over the field F. Since S is finite set in the vector space V over the field F and every subset S1, S2, S3 of the set S is also finite and is that spanning set which span the vector space V over the field F and is linearly independent, which is a basis of the vector space V over the field F, is also finite, which is a subset of the finite set S. Therefore, we conclude that there exists a basis for a finite dimensional vector space V over the field F.